Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 9, Part 2, a discussion of response models with factors and predictors, and we'll be looking at this fairly extensive example about the effect of sex and faculty rank on the salary of professors. So I'm going to approach this example from several angles. A couple just for pedagogical reasons of seeing models in different formats, but we will arrive at looking at the problem in a few different ways, specifically at the end, to try to see whether there's a relationship between sex and rank on faculty salary. So this example is collected from personnel files of faculty at a small college in the 1970s, and the data were collected to assess whether women were being discriminated against, either consciously or unconsciously, in the salary that they had. The sample consists of tenured and tenure stream faculty. So you may not know, but the way faculty ranks typically work is that you'll be hired at an assistant professor level, and you'll be on a tenure track. Some universities have tenure and some do not. University of New Mexico does have tenure, and after 5 or 6 years, typically 6, you will be assessed twice during that period, and if you're doing well with your research and teaching and service, you'll be given tenure, which effectively makes it very difficult to be fired. So you have some job security at that point, and allows you the academic freedom to pursue things without threat of being fired by administrators who may hold different opinions than you. And once you, and at UNM, the way it works is when you get tenure, you also get promoted at the same time. So tenure and promotion happens at the same time, and you'll become associate professor, and you'll be there possibly your entire career, though most professors come up in about 6 years to be promoted to full professor. Temporary faculty, such as part-time instructors, things like that, are excluded from consideration here because they're already being discriminated against. Certainly at UNM, I know that part-time instructors work very hard, teach large classes and many classes, and don't get paid that well. So it's a very hard life, and you've got to really love teaching to become a part-time instructor. Okay, to this example. We've got variables such as the identification number for each individual. There's 52 observations in this study. For sex, we've got 0 for males and 1 for females. For rank, these go in order, so 1 for assistant professor, 2 for associate, and 3 for full. The year is the number of years in the current rank. So that means that you might be an assistant professor for 6 years. So it'll start counting probably 0, 1, 2, 3, 4, 5. And then if you get promoted to associate professor, then it starts over again. Associate professor, 0, 1, 2, 3, 4, 5. Promotion to full, 0, 1, 2, 3, etc. until you retire. And so that may become of limited use to us because it's conditional effectively on rank. We have a degree, whether you've got a doctorate or something else, and the something else is typically would be a master's degree if you're faculty at a university. And then YD is perhaps going to be a more interesting variable. It's the number of years since your highest degree was earned. So if you earned your doctorate degree in 2009, the way I did, then you'll start, YD is the number of years since that degree. If some professor earned their master's degree in 2005, and that was the highest degree they attained, and they've started working, then it would be the number of years since that degree. And then finally, what the person's salary is, and that's the response variable. So let's click over to the website and take a peek at these data. Okay, so IDs are sequential. We have sexes 0 and 1, rank, year, degree, years since that last degree, and salary. And this is definitely in the 1970s. These salaries are in the 20s and 30,000 range, some quite a bit lower. Not that we're all millionaires now. All right, so we read the data set in, and notice that the structure of this data frame, everything is integers. So we're going to change some of these variables to be categorical or factor variables, in particular sex, and we'll label them male and female, rank, and notice I'm going to put them in reverse order. I'm going to let full be the baseline category, and then associate and assistant in descending order. And I'm going to label them in that same order that I have the levels in. And then the degree, whether you've got other or a doctorate, I'm going to let other be the baseline, and then doctorate be sort of an add-on from there. So it's basically a comparison of master's degree versus doctorate. All right, so now we've got labels right there in our data set. And with our factors. Beautiful. So the data include those two potential predictors of salary. We've got year and the year since the degree, and 3 factor variables. So sex, rank, and degree are each factor variables. And we want to see whether males and females are compensated equally on average after adjusting the salary for these other confounders of rank, years in your rank, and so on. In particular, we wish to know whether there's an effect of sex for each rank or not. Okay, so before we answer these questions, let's look at the data. And we've got a lot of variables here, right? We've got salary as a response variable. We don't really care about ID, but then we have 5 other variables. So we'll have to think a bit about how we want to plot it to be most informative. Is there a single plot that would be best? Well, here is a few example plots. I'm going to look at it just by, so comparing sex, male and female. Actually, this is just looking univariately at each of the predictor or each of the factor variables. So between sex, you can see basically males on average are higher than females. Okay, we don't know yet whether that is because more males have higher degrees or have higher ranks. Okay, this is just marginally. We're just giving a sense of what the data are right away. There's one female who's making a lot of money. Might be worth asking whether this is coded incorrectly. Maybe this is actually a male, or there's something else going on there. Maybe it's an administrator who's making more money than a faculty member. If we look at the degrees, at least back in the 70s, it didn't seem to make very much difference whether you had a master's degree or a doctorate in terms of the mean. And then rank, you can definitely see an increase from assistant on the right up to full on the left. And that's the way it should be. Okay, so just for pedagogical reasons, I'm going to look at a 3-way analysis of variance on the salary data. So we'll start off just by doing analysis on these 3 variables. We're going to ignore the year and the year age for now and come back to that in a later analysis. But we haven't done a 3-way ANOVA so far this semester, so here's our opportunity. Okay. All right, so my initial comment below is you can see that there's a sex effect here all by itself, right, between male and female. However, that is marginally. We don't know what other effects exist. And so my first comment here, hopefully our earlier analyses have cured you of the desire to claim that a sex effect exists, before considering whether differences between male and female salaries might be due to other factors, such as rank, in-year since degree, and so on. After correcting for those, we may find that, in fact, there is not a difference. We shall see. The output below gives the sample sizes, the mean, standard deviations of the 11 combinations of sex, rank, and degree observed in the data. There's one combination that doesn't exist. So here I'm using Plier, which I haven't used for a while now, but we'll just calculate the sample size, the length, the mean, and the standard deviation for every combination of sex, rank, and degree that exists in the faculty data frame. And when we look at that summary, we've got males at the full associate and assistant ranks for the other and doctorate degrees. And you can see some of these categories are pretty small, right? So the assistant others, there's only 3, and there's only 4 full others. This was back in a time, and some schools may still do this, that you could have just a master's degree and still be a full professor. I think times have largely changed that a doctorate is basically required for most faculty positions. For females, let me scroll down just a little bit more. We have females full professor and associate. You can see in the case of females there are no associate professors with doctorates. That's why that category is omitted. And the other categories are pretty small. 1 observation for full other, 1 observation for assistant other, only 2 for associate other, right? And 0 for associate doctorate. So there's a lot of these where we just don't have very much information. And you can see that when we have, right, this is something you already know, but you can't compute the standard deviation when you only have 1 observation. Basically because you divide by n minus 1. N minus 1, when you only have 1 is 0, you divide by 0. That's not a number. So we have actually very little information for some of these categories for both males and females, but in particular for the females. Okay, so we're going to create some marginal box plots, and we'll go back up and look at the code that created this plot in a moment. But you can see I've got all 3 variables in this single plot. This is one of the reasons I love ggplot so much. We've got salary on the vertical axis, okay, and I've made the axes go all the way down to 0. I have the grand mean as the dashed line all the way across, and then we can see the differences from the grand mean. Sex, male and female, are by color, and these are not perhaps the color you expected, but these are the default colors alphabetically. Oh, maybe that's not even the case. It's not alphabetical, it's 0 and 1. That's right. So 0 is the males, 0 is red, 1 is females, which is blue. Okay, so red is male, blue is female. Then we've got the full, associate, and assistant as facets or small multiples in this plot, and then we have got the master's and the doctoral degrees on the left and the right within each panel. And just going across, just looking maybe at the medians for these, looks like female slightly lower here, maybe slightly lower. Notice here there's no females, doctoral associates, and this bar by default ends up filling that whole space, but there's no comparison group. Here there's a slight increase, and here it's about the same. But right, all those comments are based on very small sample sizes. So our modeling is going to help us capture those features a little bit better by looking at all combinations at the same time. So I'll consider 2 simple analyses of these data. Oh, let's see, I promised you I would look at the code. So here's the code. Let me start with, okay, I'm going to assign the salary to the response variable y. Let me make this bigger. The degree to x. Okay, so that was other and doctorate, which is other and doctorate on the x-axis. Page back up. Where do I want to, let's see. I put a horizontal line at the mean that's dashed. Okay. Then I create box plots, and plot those. I also plot the individual points, and we saw those, right? Box plots and individual points. Page back up. Facet grid by rank. Okay, so I have nothing separating the different rows, but ranks are for columns. So if I page back down, I've got full and associate by the columns. So it's those small multiples. And then I'm setting the y-axis to go all the way down to 0, and then the maximum of the salaries. And the last thing here is up here at the top, actually, position dodge. So if I page down for a moment, and zoom out just a tiny bit, the default here is that these boxes would lay on top of each other. And so I'm choosing to dodge them, meaning they're going to move to the left and to the right so they don't lie on top of each other. And so the dodge gets them to be side by side. If I page up again, position dodge 0.75. So the 0.75 here indicates that the horizontal spread takes up 75% of the width of the large column in the plot for, let's say over here, for doctorate. So doctorate basically takes up the right half of this small multiple gray box, and I've got a little bit of space to the left, a little bit of space to the right, and the middle 75% is how wide those plots are together. So that's the dodge 0.75. You have to, the way I've chosen to do it is I create that and I put it into PD for position dodge, and then I have to find where I use that. Here it is. Geom point position equals PD for position dodge. So that makes it so that the points, so the box plots would have been dodged already, but the points would have laid all on top of each other in the center. And so here I'm dodging the points to the same degree that the boxes were dodged. Okay. Let me page back up. Anything else? I put a label on there. Great, there's a title. And that's the plot. How did I make this plot? When I was thinking this plot out, I actually took out a piece of paper and a pen, and I thought about how I would plot this. And I drew it first, and then I coded each of the elements for the plot. All right. Now, I'll consider two simple analyses of these data. First, the first analysis considers the effect of the three factors on salary, and then the second analysis will consider the effect of the predictors. Okay, so I'm doing this analysis only for illustration. Typically, I would just throw all the predictors in there, at least the ones that I wanted, and work on the analysis. But I just want to show you what a three-way interaction looks like. So the full model for a three-factor study includes the three main effects, all the possible two-way interactions, and then the single three-factor interaction. So if I have sex S, degree D, and rank R in the model, then here is the way the model can be written. Okay, so I've got, maybe grand mean or intercept. Okay, there's different ways to parameterize the model. We have the main effect for sex, main for degree, main for rank, and then the two-way interactions, and there's three of those. 3 choose 2. And then there's 3 choose 1 or 3 choose 3. There's one way to have the three-way interaction. Okay, so we know what the main effects and the two-way interactions, how to interpret those from previous examples. The three-way interaction is really tricky, and actually there's going to be lots of terms that this expands out to when you think about all the indicator variables. But this three-way interaction will give us the ability to estimate every mean for every combination of sex, degree, and rank so that the model predictions are the same as the observed means that we got from the data. And that's important when when basically everything depends on everything else and there's really no structure in the data, but there's just sort of almost randomness in terms of the sex, degree, and rank effect on the salaries. Okay. Three-way interactions are hard to interpret. Two-way interactions are fairly hard to interpret. Three-way is even harder. Okay, so if you look at two levels, at the two levels of degree separately, then a three-factor interaction is needed if the interaction between sex and rank is different for the 2 degrees. Okay, my head's sort of spinning a little bit from how complex that sort of is. So we'll do backward elimination, just as we have done throughout this semester. And all right, so I'm just going to use the AIC criterion in the step function for this. All right, so let's put the full model. So here's the linear model of salary versus sex star rank star degree. So these stars expand out to be all the main effects, all the two-way interactions, and the three-way interaction. So there's a lot there. But then as soon as I do that, fit that linear model, it goes into full, and when I try to look at the result, I suddenly get an error in the ANOVA 3 LM, etc., singular.ok. There are aliased coefficients in the model. And so what's happening? Let me scroll down just a little bit. And when we look at, is it all going to fit enough? Let me see. Okay, it fits enough. So here's the coefficient table. Okay, it goes all the way down to there. And one of the rows here has NAs. And that actually makes sense. That is for females, associate doctorates. And as we saw before, that was a combination of factors that had no observations. So we have no data. Therefore, we have no information to make an estimate. And so this full model that gives us all the main effects, all the two-way interactions, and the three-way interactions, we don't have enough data to estimate that model. Coefficients, one not defined because of singularities. Singularity in this case is that we've got basically one category that has no observations. It's related to whether the design matrix is invertible or not. And in this case, it is not. Okay, so what to do? Well, the main thing we can do is simplify our model. So I believe that's what I probably do next. By the way, one short comment here. The row, because we've got these variable names that are super long, the output wrapped. So notice we don't have our stars on the right, to the right of our p-values over there to the right. Instead it wrapped and we have our stars here. Okay, it redoes the row labels, but just wanted you to know why that looks so strange. All right, so I'm going to start with that full model, which is fine, and then I'm going to do backward selection. The model, you can't really fit all the parameters of that model, but once we start backward selection, we're going to start getting rid of model coefficients, and therefore our model will become simple enough that things will start to work. Okay, so we're going to use stepwise procedure and put that into AIC, and let's see, salary is the full model, and none. This suggests that we should drop the highest order. Actually, it suggests that we should stay where we are, but the next best thing is to drop the three-way interaction. And basically in this case, because the full model could not be fit, the step procedure didn't work. We actually didn't get going. So let's manually, okay, so here I'm going to set the full model to the reduced model. So LM faculty factor.red is for reduced, and I'm going to update my reduced model by subtracting the three-way interaction. And let's just take a look at that reduced model. Here's all the two-way interactions, and all the parameters here could be estimated. So what's sort of interesting here is that we don't have female associate doctorate as a category. However, this model can make a prediction for what that cell would be. Okay, we don't have any data, but the model will make a prediction there without any trouble. Just as in a regression line, we've got data, you know, as at certain x values, but we can make predictions of x values that aren't in our data set. Same thing here. All right, let's do AIC as backward selection. Okay, backward, and we're going to output the F statistics and their p-values, and we're going to start with the main effects and two-way interactions. Looks like we can drop age and rank, and then we can drop the sex degree interaction. Now notice, right, we've dropped the two effects, both sex rank and sex degree, that depended on sex. And the next one allows us to then drop the main effect because there's no higher interactions that have sex in it. So then we can drop sex, then rank, degree, and then degree. Oh my goodness, our model sure is getting simple. And then that's it. And we're left, looks like, with only rank in the model. So let me scroll down a little bit, and here is our final. I'm going to move our reduced into our final model and look at the ANOVA for it, and it only has rank in it. So the best model, parsimoniously based on these three variables, is rank. There's no sex difference, and there's not even a difference between whether you have a doctorate or not. So here we've got our intercept. This is for full professors. If you have an associate degree, you earn 6,000 less, and if you have an associate rank, you're 6,000 less, and if you're assistant rank, you're about 12,000 less. I may have said that wrong, but you get the point. R squared is about 75% of the variability. At this point, of course, we would check out all our model assumptions and so on, but we know we've focused on model assumptions. I want to focus on some of the other concepts here. So we can use LS means to give us some output here. In particular, if I scroll up a bit, okay, the ANOVA table suggested that rank, as a 2-degree of freedom test, there were differences between ranks. So now we might be interested which pairs of ranks are different. We know from our summary, when we look at the coefficient table, that here is our full professors, and these p-values compare whether the associates are different from full and assistants are different from full. So those are both true, but we don't see here whether associates and assistants are different from each other. So we're looking back now at a previous chapter, I think chapter 5, that dealt with all these factor models, and we're now doing full pairwise comparisons. So full and associate, full and assistant, and associate and assistant is also differs by about $5,400. Okay, so don't want us to forget the things that were so important to us just a month ago. All right, so what have we learned? at least in this analysis, looks like sex is not predictive of salary once you account for other factors. Okay, so recall this was only the first way we're going to look at this data, and just to illustrate what a three-factor ANOVA with backward selection looked like. And it wasn't ideal because we didn't have the one category, the female associate doctoral, we didn't have any observations in that combination of factors. But the biggest flaw here is that we don't know what the effect of the, how long you've been in your, either had your degree or been in your faculty rank in this analysis. So time-wise, this seems like a good place to take a cut in the video, and we'll come back and we'll look at a more comprehensive analysis that uses the years in addition in the model.